Okay, welcome to a brief podcast dealing with the application of integration, namely areas under a curve. You'll notice here that in your formula booklet there are two references to the area between a curve and the x-axis. This one here deals with when the y values of the function are above zero, namely positive. So you've got an area under a curve between some a and b value nicely defined as the integral from a out to b of that function with respect to dx. A little bit further on in your formula booklet, there is an area under a curve more generalized, because you can have an area under a curve that is negative, as it turns out. So when you're below the x-axis between some a and b, that's going to be negative, and all this feature is doing with the absolute value is ensuring that it becomes positive. So your GDC for paper 2 is going to be your best friend. Something as simplistic as let's find the area under the root x function between x equals 2 and x equals 7. If you go to second calc in your GDC, and you've got this menu here, it's feature 7, referring to the integral of some f of x dx. And you simply have to put in and follow through the menu of sort of left value, right value, and then it'll hand you for free the area under the curve, which for paper 2, you'd be doing a quick sketch of this and simply write down 10.5 to 3 sig figs, and you get full marks for that. So if you think about the area under the curve in more of a paper 1 sense, of course, you'd be integrating x raised to the 1/2 dx. And of course, the integral of this would be x to the 3/2 divided by the 3/2, or namely 2/3 of x raised to the 3/2, or the 1.5 power. So what I've done to convince you over here, you've got upper and lower bounds of 7 and 2 respectively. Here they are being raised in each case to the 3/2 power and subtracting them. And then because you would have to take 2/3 of that, I multiplied that by 2/3 to get the same value that you saw previously given by the GDC directly. We can apply this kind of reasoning to any one of a number of functions. So here is our classic 1/x function, and the integral of 1/x dx, you'll recall, is the natural log of the absolute value of x, which just safely ensures that the natural log has to act on positive values only. And so upper bound of 5/2, subtract from that the lower bound evaluation at 1. You, of course, recall that the ln of 1 is 0. So one form of an answer could simply be the ln of 5/2. IB might ask you to say, like, find the answer in a paper 1 sense of the natural log of some a over b, write down the values of a and b. You can also equivalently say, using the logarithmic properties, that the log of a quotient is just the difference between those two values. So what are we really talking about here? We're talking about the area under the curve from x equals 1, as you can see down here, out to 2.5, which is right here. And so that area ends up being given directly by your GDC, about 0.916 or so. And I've just put under here to remind you, in a paper 1 sense, ln 5 minus ln 2 ends up being exactly the same value. So once again, it's confirmed. Finally, let's show that the integral from 3 out to 5 of something like e raised to the 1/2 x dx looks like this. This, of course, would be a requirement for a paper 1. The next slide will have the full development of that. What I thought I would do is just indicate to you that if you take what looks rather abstract here, of course, keeping in mind that e is roughly 2.7-ish, if you end up just cranking this out on GDC, you get 15.4-ish. And lo and behold, when you put into your GDC y is equal to e raised to the 1/2 x, and simply use that second calc feature 7 for finding the area under that curve between x equals 3 and x equals 5, you end up seeing that the GDC confirms that value for you. So let's close with a brief look at that relative to paper 1. If you were asked to show that this integral is in fact this exact value, recall language that I used to use was something like what controls the problem in a substitution type sense. This exponent controls it, so let u equal 1/2 of x, and then when you take the derivative of this, so du dx, namely the derivative of u with respect to x is 1/2. You can split the operators, and keep in mind that these operators become quite powerful and have lots of meaning within the context, so you'll be shifting over or substituting from an x world over to a u world. And so e raised to the u is the choice that you made, and of course dx has to leave the system, and dx, by virtue of what's happening over here, dx is just equivalent to twice du, and so this dx gets replaced with twice du, where we've already pulled the 2 through the integral symbol, which you can safely always do. Then the integral of e to the u du, a la what you have from your formula booklet, which of course says the integral of e to the x dx is just itself. Well, here you've got u happening in terms of that integral, so twice the e raised to the u, back substitute on what u actually is, and so here you are with the plus c. And so the integral of this, as requested, ends up looking like this. And of course, at the top and lower ends, you'll be doing the subtracting. Keep in mind that this constant will, of course, fall out and is not even technically required for you to be writing it down, although you can safely write it down so you never forget in other contexts as well. Factoring out the e raised to the 3/2 leaves you with that final result. So that's it for now, for just a quick intro for basically areas under curves for any series of functions, especially with the GDC paper 2 type approach. Thank you.